Morning dear students, today I will be discussing on time domain representation for LTI systems. So this topic will be under module number 2. So first we'll know what is LTI system or what exactly the LTI system is. And here is the definition. The system which satisfies linearity and time invariance are called linear time invariant system. So that system we call it as LTI system. You have already studied the time invariance and linearity. This linearity depends upon the superposition theorem, and time invariance depends upon input and output of any systems. If any system satisfies the superposition theorem and the input and output variations, then that system will be considered as linear time invariant systems. So, and these LTI systems can be represented in time domain representations, and these are the different LTI systems in time domain. So first is in terms of impulse response, second is difference or differential equations, third is block diagram representations. These are the different methods we're going to analyze the LTI system. And the next is impulse response representation for LTI system. So what is this impulse response representation for LTI system? Impulse response is nothing but a sudden response for any linear time input, linear time invariant systems. And here is the definition. The definition is like this: the linear time invariant system can be represented in terms of its response to any unit impulse, so which is known as impulse response of a system. So in a simple way, it is a response, it is a sudden response. Impulse means it's a sudden response for an input. So that is what the impulse response representation for LTI systems. So in this chapter we will be describing the different time domain representation for LTI systems. For example, the different representation that relate the output signal to the input signal when both the signals are represented as a function of time. So one of the primary reasons for LTI systems are easy to analyze, that they exhibit superposition theorem. So I have discussed about the superposition theorem, which will come under the linearity. So therefore, if we can represent the input to the LTI systems in terms of linear combination of a set of basic signals, so then we can find output of the system. That is similar to that of Bibo stability or Bibo stable. For bounded input you need to get a bounded output, or for limited input you have to get a limited output. That relates with the time invariance and the linearity, which is related with the superposition theorem. Next we'll go for representation for discrete time LTI system in terms of impulse response. We just remember these two equations, so that is enough. So there is a big derivation that is not required for you. You just remember these two equations, that is y of n is equal to summation k is equal to minus infinity to infinity x of k and h of n minus k. So in terms of discrete time samples, so this will be y of n is equal to x of n convolution. This star indicates the convolution h of n. So here I have written x of n stands for input of a system and y of n stands for output of a system, and h of n obviously it is a impulse response. Till now we are talking about the impulse response. Here it comes the impulse response. H of n represents the impulse response of any system. So you just remember these two equations to solve the problems. So now I will take up a problem, a simple problem. A discrete time LTI system has impulse response h of n as shown in the figure. So using linearity and time invariance property, so determine system output y of n if input x of n is given by. So they have given x of n. Here is x of n. This sketch they have given x of n is equal to this sample or this signal. This is a discrete time sample, and also they have given x of n is equal to 2 into delta of n minus delta of n minus 1. So this we need to sketch. This sketch they have already given. So given is x of n is equal to 2 into delta of n minus delta of n minus 1. So how to draw this sketch, or how to sketch for this equation? So we have delta of n. We have a sample that is which is existing at 0, whose amplitude will be 1. So the same sample I am using here. delta of n, 2 into delta of n. 2 indicates the amplitude. Here in a basic signal and the amplitude is 1. Now you make it 2 because they are talking about the amplitude 2 and delta of n signal. Delta of n at 0 its amplitude will be 2. Now it is 2. In basic signal it was 1, now it is 2. So this is your 2 into delta of minus n. So now you sketch delta of n minus 1. So already we are having delta of n. So delta of n, the signal which is there at origin and whose amplitude is 1. Now you shift the signal towards the right because delta of n minus 1. So n minus 1 is equal to 0, n is equal to 1. So if it is positive, you have to shift it towards the right. So shift the signal towards the right. Delta of n minus 1, the signal should be shifted towards the right by one sample. Look at this, at 1 the signal is shifted, and minus sign indicates the negation or a reflection or a negative axis. The signal has to appear at the negative axis. That's why I have written it in downward. It is minus, shift and minus. So this is what x of n into 2 into delta of n minus delta of n minus 1. So now we got h of n and x of n. Now you start comparing. So first you take this sample, only one sample you consider, that is at 0, its amplitude is 2. I have taken only one sample. In this sample I have not considered this minus 1 amplitude sample. I have considered only the sample which is there at 0. So now you take this 2 and multiply with all these amplitudes. This 2 into 1, you will get 2 at minus 1. Next this 2 into 3. Why I am multiplying? Because we are having an equation that is x of n into h of n. That's why I am multiplying both the signals. Use that equation, that is x of n convolution h of n is equal to y of n. So x of n convolution h of n. H of n is here and x of n is here. So now you multiply this 2 into x of n into h1 of n. 2 into 1, you will get 2. Again 2 into 3, 2 3s are 6. At 0 it is 6, and 2 2s are 4. At 1 it is 4, and 2 into minus 1, so you will get 2. So minus 2. Wait a minute. At minus 1 it should be minus 2 only. 2 into 2 will get 4. 4 into 2 is 6. First is 2 and 6. 4 minus 2. Yes, so this will be, sorry I made a mistake, this will be minus 2. This will be minus 2. Now once again I will show you. So 2 into 1, 2. 2 into 3, you will get 6. 2 into 2, you will get 4. 2 into minus 1, you will get minus 2. And 2 into 1, get 2. At 3, you will get 2. 2 into 1, you get 2. Next one more sample is there, that is at 1, the minus 1 amplitude is minus 1. You just multiply this amplitude with this basic x of n. So minus 1 into 1 will get minus 1, minus 1 into 3 it will be minus 3, and minus 2 minus 1 into 2 get minus 2, and minus 1 into 1 will get minus 1. But the condition is you have to shift the signal. First you shift the signal towards the right, the same signal you shift towards the right. Why you have to shift? Because the same signal has shifted. First it is at a delta of n, and then it is shifted to delta of n minus 1. That's why this signal has shifted to 1. Now after shifting this signal, it can be written like this. You can write the same signal. I'll show it here. So signal is there at minus 1. Now it has to shift towards at 0. At 0 its amplitude is b. Its amplitude will be 1. Signal starting position will be at 1. Next, so the 0th signal will shift on 1. So at 1 it will be 3. At 2 it will be 2. The same signal is shifted on 2. So 2 it will be 2. At 3 it will be minus 1. So is 1, 2, 3. At 3 signal it will come on 4. So this is what the signal is. Now you multiply this delta of n minus 1 to this equation. 1 into minus 1, minus 1 into 1, amplitude is 1, you will get minus 1. Next minus 1 into 3, you will get minus 3. That's what I have written. And minus 1 into 2, you get minus 2. Next minus 1 into minus 1, you will get plus 1. Here is plus 1. Next at minus 1 into 1, get 1. So this is what the final sketch. And next you add these two samples. Add these two samples and also add these two samples. If you add these two input samples, that is x1 of n and x2 of n, this is x2 of n, you get 2 and 1. Now we add these two signals. The starting point of the signal is at minus 1. So among these two signals, the only one signal is existing, that is y1 of n. In case of y2 of n, there is no existence of signals. Next at minus 1 it will be 2 only, because there is no signal in case of y2 of n. So that's why I have written only one signal, that is at minus 1 the amplitude of the signal is 2. Now at 0 the amplitude of signal is 6, but in case of y2 of n, at 0 the amplitude of the signal is minus 1. So 6 minus 1 you will get 5, that is plus 5. So next at 1 it will be 4, and here it is at 1 it will be 1. So 1 plus 4, get 4 minus 4. At 4, at 1, you just go on adding all these signals. Look at this at 2, 2, minus 2, minus 2, minus 2 and minus 2 will get minus 4. This at 5 there is no signal. You just go on adding these two signals. You just add the amplitudes with respect to time scales. At 1, at 0, at 1, at 2, 3, at 4 and 5. Then you will get this final sketch. First thing is you sketch for the given equation and then split the sketch 2 and 1. Next you multiply this 2 into this x of n, x of n into h of n. Next case the signal has shifted towards the right, That's why the main signal has to shift towards the right. So this is what I have done here. Then you multiply this x2 of n to y2 of n. This is actual y2 of n. Then you will get this sketch. Next you add these two sketches and also these two sketches. If you add these two sketches, you will get this, and if you add these two sketches, you are going to get this. You just have to add the amplitudes. Add the amplitudes with respect to the time. Thank you.